In this video, I'll be teaching you about depth first search algorithm, also known as DFS. Graphs are interesting structures with many applications, most of which would require us to process vertices and edges in an orderly manner. In DFS, the traversal starts from a particular vertex and proceeds as deep as possible, neighbor to neighbor, before backtracking. Now, let me show you this with respect to a maze. Now, assume this to be the starting cell and this as the destination cell, and we are required to travel through the maze to reach the destination cell. One of the most intuitive, logical and programmable ways to solve this particular maze would be to actually follow a path and then proceed as far as possible until we reach an obstacle, and when we reach an obstacle we can backtrack to the previous cell and we can search an alternate path. Now let me show you how I've done this here. So the convention that I'm going to use is that the highest preference is given to moving a block downwards and then to right and then up and then left. So starting from here, following the convention, this is the path that we will get. I'm following the convention that I mentioned here. So as you can see here, I have reached an obstacle and I cannot proceed any further. So now I can backtrack. So when I backtrack to the previous cell, it doesn't really improve anything, and hence I will backtrack again. When I backtrack here, I remember when we were at that position, we had two options, either to move right or to move down, but we chose to move down because of the convention. So now we will move right to choose the alternate path. So, and now when I follow the convention again I hit the obstacle. So now again I'll backtrack twice in order to find a suitable alternate path. And now following the convention this time will take me to the destination cell. So what we performed here was actually a depth first search, because we tried to proceed as far as possible along a given path, and when we fail to reach the destination or when we reach an obstacle, we would backtrack to a previous cell and we would try to proceed in an alternate path. Now let me explain the algorithm. So here I have two methods. So the first method takes the input as G. So G is a graph which can be represented as an adjacency matrix or an adjacency list, right? So capital V is a set of all vertices in the graph G. So we are going to use a global variable count, which will be initialized to 0. And then for every vertex in the set of all vertices of the graph, we check if the particular vertex is has already been visited. If it is unvisited, then we will call the auxiliary function with respect to that vertex. So what the auxiliary function does is that it recursively calls itself with the parameter changing of time. So the new parameter will be an adjacent vertex to the particular vertex V here. So I'll show you here again. So in this auxiliary function, initially we will be incrementing the value of count, and then the vertex V will be updated with that value. It will be marked with the value. Alright? And then we have an iteration here. So what this iteration does is that, so it iterates through all the vertices which are adjacent to vertex V, and then it checks whether that particular vertex W is unvisited, and if it is unvisited, it will recursively call the same function. It will recursively call the auxiliary function with respect to that adjacent vertex. So now I'll be explaining you this algorithm with the help of an example. It has 10 vertices A through G. And because DFS algorithm is a recursive algorithm, so and we know that recursion uses a system stack to keep track of parameters and the values of the functions between recursive calls. I've drawn a system stack here to help you visualize better. So we'll start traversal from vertex A because of alphabetical order. Alright, so initially A will have the value of count as 1. Alright, and because A is the top element of the stack, A has 3 adjacent vertices, E, C and D, out of which we will select C because of alphabetical order to break the tie. So this is the convention which I will be using throughout the example. So the next element to go in the stack will be C with the value of count as 2. So now C has D and F as unprocessed vertices, whereas A has been visited already. So now D will enter the stack. Now both of these vertices, both of these adjacent vertices A and C have been visited already, and hence D can be popped out from the stack. Now after D has been popped out from the stack, the top element of the stack is C. and C has 3 adjacent vertices A, F and D, out of which both A and D have been visited already. Only F is unprocessed. So now F will enter the stack with the value of 4 because the previous value of count was 3. Right? So now F has 2 adjacent vertices E and B, and we will be choosing B, which will enter the stack with the value of count of 5. And B has only one unprocessed vertex E. Yeah. So now E has 3 adjacent vertices A, F and B, all 3 of which have been visited earlier, and hence E can be popped out from the stack. After E was popped out from the stack, the top element of the stack is B, and B has 2 adjacent vertices F and E, both of which have been visited already. Hence B can also be popped out from the stack. And similarly with F, all the 3 adjacent vertices have been visited already, and the same follows with C because A and D have been visited already, and the same follows with A. So we aren't done with the traversal yet because we still have 4 more vertices to process. So starting from vertex G, so G will enter the system stack with the value of 7 because because the count value before G was 6 with respect to E. Right now G has 2 adjacent vertices H and I, and we'll be choosing vertex H to go into the system stack now. So this will become H8. Right, and H has 2 adjacent vertices G and J, out of which only J is unprocessed. So now J will also enter the system stack. Yeah, and now J has only one unprocessed vertex I because H has been processed already, and I will also enter the system stack. Yeah, and because both the adjacent vertices 2I, G and J have been visited already, I can be popped out from the stack. And after I was popped out, the top element of the stack is J. And similarly, with J also, both H and I have been visited already, so J can also be popped out from the stack. Alright, so and the same follows with H because both G and G have been processed already, and the same follows with G because both the adjacent vertices have been visited already. So with this, the system stack is now empty, and all the vertices in the graph have been processed and visited, and hence the traversal is completed. And the traversal for this particular graph is A, C, D, F, B, E, G, H, J, and I. That's it. Thank you.